Good morning, all the students.
Good morning, ma'am.
Good morning. Today we'll start our last concluding lecture under module 4. So that from Monday we can freshly start our fifth module. Okay, in the last class, we have seen what are Bayesian belief networks. When some conditional dependencies can be implied on some subsets of variables, and some variables are assumed to be conditionally independent. In that cases, can we draw the descendants or the successors from the parents that are known? Means what is the probability of the child node occurring if the parent node is given, right? That will help us to actually draw some probabilities about variables which are not observable. Means in some cases we can measure some variables, but some variables can't be measured. They are called as unmeasurable variables, or they are also called as soft variables. Hard variables means you can measure them easily, but soft variables can be derived from the measurable variables. They are called as unmeasurable or unobservable data, right? In such cases, we can use these Bayesian belief networks in order to attach some probability so that we can say with some confidence that this is the probability of the child if the parent node already exists. For that, I have given you an example of preparing a hot cup of coffee on a rainy day. Means a hot cup of coffee is treated as the child node to the parent node rainy day. In that case, probability of rainy day will increase the probability of making hot cup of coffee, right? That is how you need to understand Bayesian belief networks. Why we assign this word belief networks is we believe in the probability of the parent occurring so that we can calculate with some probability the child node's occurrence also. Got it? That is the use of Bayesian belief networks. For that, we have represented it in mathematical format, and we have also seen, given the conditional probabilities of the parent nodes, when they exist and when they do not exist, or when they occur and when they do not occur, how to calculate the child nodes probability. That is explained to you in the last class. Say if you take campfire, setting up a campfire and not setting up a campfire. When the storm has occurred and the bus tour group has arrived, when the storm didn't occur but the bus tour group has arrived, when the storm occurred but the bus group didn't arrive, and when the storm didn't occur and the bus tour group didn't arrive. These probabilities are given in the table for us. In that case, we can calculate the probability of setting up a campfire and not setting up a campfire. So what we understood from this table is if the parent nodes probabilities, joint probabilities, see both of these occurring together, both of these, one of them occurring together and one of them not occurring, right? In that way, if joint probabilities are given, then it is easy to calculate its child's probability, right? That is what we understood from the Bayesian belief networks. In today's class, we are going to see the expectation maximization algorithm, or sometimes it is also called as estimation maximization algorithm. Okay, this is referred by these two names in many places. So do not get confused. You can call it as expectation maximization or estimation maximization algorithm, right? Now, let me give you an outline of this algorithm before going into the mathematical concepts, because if you have a clear picture of what is going to be, calculated, or what is going to be derived by using this algorithm, then it will be easy for you to understand the mathematical concepts, right? Remember, though the mathematical concepts are a little bit difficult to understand, in this case, the example taken is like that. But I'll explain this expectation maximization algorithm to you with a simpler example so that you will understand the concept. Later, we'll see what is given for you in the reference book, because that also you have to understand, right? Okay. Now, what is this expectation maximization algorithm or estimation maximization algorithm? In this case, when do you actually use this type of algorithm? Say, in some cases, when the data set is given to you, or when you're capturing the data into a data set, some data may be observable, some data may be measurable, but some data you can't measure, right? As I said yesterday, force is equal to mass into velocity, acceleration. Yesterday I gave you as velocity, right? It is acceleration. Now in this case, consider F can't be measured, and only mass and acceleration can be measured. Or you just take them as separate variables, mass, acceleration, and force. Don't consider the equation still. Now, in this case, assume that mass can be measured and acceleration can be measured, but F is not measurable. In that case, we can derive F as product of mass and acceleration. In this case, these two are called as hard sensors, hard variables, and this is called as soft variable. Why? Because you're not directly measuring it, but deriving it as a equation of the measurable variables. Right? Now, in the same way, when you're capturing data into your data set, if you want to capture the data under various parameters. Now, among those parameters, some of the parameters are directly observable. You can observe the sample points at hand. Say you are studying the performance of students. Okay. Now, in that case, some parameters are directly measurable. You can measure them. But say some parameters are not directly measurable. We call them as unobservable data. Now, these unobservable data can be directly measured from observable data. Give to the training set already observed data, let it learn from already observed data so that it understands the distribution of data. Say most of the values are having very less value and most of the values are having greater values. Most of the parameters are having lesser values and most of the parameters are having greater values. No. One second. Yeah, I'm just telling the other way. Do not get confused. Most of the values we take for the variable lie in this range. Lie in this range in the middle, and very less number of values. Yeah, I told you the other way. Very less number of values will have very less value or very high value for that variable. But most of the values fall in a average range. That is called as normal distribution, right? I'm explaining again. If you take a distribution like this, distribution means you just plot the data points, that's all. Say there is a variable age, or you take weight, that will be more appropriate. You take a variable weight. Now in a classroom, very less number of students will have very less weight and very less number of students will have extreme weight. But most of the students will have an average weight falling in this particular range. Say if you take the weight as 40 to 100. Now very less number of students in a PG course has 40 kgs weight and 100 kgs weight, but most of their weights fall within this range, right? 50, 60, 70, 80, 90. Right? That is called as normal distribution. Now, when a parameters values are given, when a variables or attributes values are given, there is some data that is already existing. Now the learning system will learn from that data what is the distribution of the data. Whether the distribution is a normal distribution or whether the distribution is a skewed distribution. Skewed means most of the values are having, most of the parameter values are having higher values and very less number are having lower values, like that. Okay, this is skewed. In some cases, you may get a value like this. This is also skewed, right? Means most of them are having extreme values in this case, and very less number are having lesser values. Okay, in this case we call them as skewed values. This case and this case we call the distribution as skewed because there is no what say normal distribution between the values of the parameters, right? In that case we it is actually, we say that the samples that are taken are biased because most of the values are being packed into a particular area or region. In this case, they are packed into this region, and in this case, they are packed into this region. That is why we call them as skewed. Right? Now, when you're capturing the data into the data set, under the parameters, under the attributes, some of the attribute values are known. Assume that some of the attribute values are known and some of the attribute values are not known. Okay, now the learning system is given the known values. Now it will be trained on the known values. Once it is trained on the known values, it understands whether the data comes from a normal distribution like or a skewed distribution like this. It will understand, right? It has set of values, right? Under weight, it has some 100 students data, among which 80 students data is known and 20 students data is not known. Now, the training the learning system is given with this 80 students data. It will understand from these 80 students weight that this data comes from a particular distribution. Distribution means most of the values are having an average range and very less values are having extreme values, minimum and maximum. In that case, it can generate the other 20 values. It can be used to generate the other 20 values, right? So by using this expectation maximization, what you're doing, first you're expecting the values of unobserved data. Unobservable data, you estimate their values, expect their values, guess their values. And in maximization case, in maximization step, you try to maximize their probability of occurrence in the data set. Means you're finding whether the learning system's guessing is correct or not in the second step. You're trying to maximize the expectation that is done in the first step. Means you're guessing the 20 students weight here and whether this 20 students weight, guessed weight is appropriate to be in accordance with the hypothesis made about the students. If that hypothesis is being true, is reaching its accuracy, in that case, it has reached a point of convergence. Means you iteratively do this process. Expectation maximization algorithm is an iterative process. In the first step, you guess the values of unobserved data, expectation step, and in the maximization step, by seeing these guessed values, the algorithm have to understand whether it is the data is in accordance with the hypothesis or not, which will increase the probability of that hypothesis, which will maximize the probability of that hypothesis becoming true with this guessed data. If it is not maximizing, then in the next iteration, expect the new values of the unobserved data. And again, in the second step, maximize the likelihood of the hypothesis by using this data. Still, the data is not being suitable to the hypothesis. Iterate again. In the next iteration, again expect the variables values, unobserved variables values. Now, these values are maximized. These values are considered, these guessed values are considered to be to maximize the likelihood of the hypothesis. If the hypothesis likelihood is maximized, then it has reached a point of convergence. means you have reached the correct expectation of the unobserved data. Stop there. Okay, so what you did in this case, from the observed data, you're making a system to guess the unobserved data and optimizing that expectation in order to maximize the likelihood of the statement made about the data, whether that data is suiting the hypothesis or not. If it is not suiting, in the next iteration, guess different values for the unobserved data. Again, that data has to be checked whether it is maximizing the hypothesis likelihood. If it is maximizing, then that will be your endpoint. You can stop the iterations of this EM algorithm. Did you understand? This is the basic idea behind expectation maximization algorithm. Simply, if you want to specify, initially you see what are the observed. I'll just specify that in 4 steps. Okay. In the first step, you see the data that is observed, hand it over to the learning system. Now, this learning system will expect the values of unobserved data. Now, this unobserved data's guessed values are checked whether they are in accordance with the hypothesis to maximize the likelihood of the hypothesis, to make it as maximum a posteriori hypothesis. If it is not suitable, guess the values again in the next iteration. If the values are suitable, stop it there. Okay, this is the core idea of expectation maximization algorithm. Now, in many practical learning settings, only a subset of the relevant instance features might be observable, right? In this case, say this is observable and this is observable in this network, but campfire is not observable. It can be, that probability of campfire can be calculated from storm and Bastur group, right? Now, this thunder can't be measured. Say probability of thunder can't be measured. But once its parent's probability is known, it is easy to calculate the probability of thunder. That is what is being explained in this first point. In many practical learning settings, only a subset of the relevant instance features might be observable and some other variables might not be observable directly. For example, in training or using the Bayesian belief network in the figure, what we have taken, we might have data where only a subset of the network variables storm, lightning, thunder, forest fire, campfire, and Bastur group have been observed. Now, many approaches have been proposed to handle the problem of learning in the presence of unobserved variables. So there are many approaches like expectation maximization algorithm, Bayesian belief networks. There are some algorithms like this which will help us to handle the problem of learning in the presence of unobserved variables. Now, if some variable is sometimes observed and sometimes not, sometimes we can measure them. Sometimes we can't measure them. As I said, out of 100 students, 80 students' weight can be measured. But 20 students, maybe they are not regular, or maybe on the day when the measurements are taken, they are absent. Their data is not available. In that case, you can make the system to learn the distribution of the data from 80 students' data and let it guess what would be the other 20 students' data. Easy, right? The basic idea is easy. Now we are going into a little bit of complexity by taking an example of 2 distributions occurring. Now, many approaches have been proposed to handle the problem of learning in the presence of, yes, unobserved variables. Now, if some variable is sometimes observed and sometimes not observable, then we can use the cases for which it has been observed. Say 80 students data has been observed, to learn to predict its values when it is not, to predict the values of 20 students' weights, as I said. Now, the expectation maximization algorithm is a widely used approach to learning in the presence of unobserved variables. Okay, this is most prevalently used, most frequently used algorithm, EM algorithm, in order to predict the values of unobserved data given the values of observed data. observed data values have to be given, then it can guess unobserved values of the variables. Now, the expectation maximization algorithm can be used even for variables whose values is never directly observed. Sometimes, in some extreme cases, say some of the variables data is not at all observed, the data is not at all captured. Then also this you can use this EM algorithm, provided there is a condition, provided the general form of the probability distribution governing that particular governing these variables is known. Means if you know the distribution of the data governing these variables, means say determining these variables, in that case you can guess the unobserved variables, though single variable value is also not given. Say storm values are available to you, bus tour group values are available to you, but none of the campfire values are available to you. In that case, if the distribution of,
Ma'am,
yes,
ma'am, PPT is not available, visible, ma'am.
not visible.
Yes,
One
ma'am.
second. Now, Naina?
No, ma'am.
No.
Yes, ma'am. Now it's visible.
Okay. Okay, now in this case, if storms data is available, bus tour groups data is available, and campfire data is unobservable, it is not available. In that case, if the learning system is able to understand the distribution of data in storm and the distribution of data in bus tour group, it can guess the values for campfire. Did you understand what I'm talking about? If some of the values of campfire are available and some of the values of campfire are not available, learning system will learn from the available values of campfire and it will determine the unavailable values of campfire. That is one case. Suppose none of the campfire values are available. In that case, it will try to understand its parents' value distribution, its parents' data distribution. And from learning from the parents' data distribution, it will be able to guess the distribution or values of the campfire. That is the second case. When partial values are known, the learning system will learn from the partial values to guess the other unobserved values. And in the second case, if none of the values of a variable or attribute are known, it will try to understand its parents' value distribution, attribute values distribution, and try to guess the child's values. Okay, that is the second case. Now let us see, let us take this help of this expectation maximization algorithm in estimating the means of k Gaussians. What is Gaussian distribution? It is the other name for normal distribution. You need not get confused when you see Gaussian normal being used interchangeably. Both are same. A Gaussian or a normal distribution will be in the form of a inverted bell curve. Okay, say in India, very less number of average weight of the Indians lies between this particular range, right? Very less number of Indians will have underweight and overweight. Most of the Indians' weights are in this range, acceptable range. Okay, in that case, we call it as a normal distribution. There is no skewedness in the values. Okay, it is equally distributed across. So this is called as normal distribution. Now consider a problem in which the data D is a set of instances. You know that D is used to represent the set of instances generated by a probability distribution that is a mixture of k distinct normal distribution. Means you are taking a probability distribution now, example of a probability distribution that is a mixture of k distinct normal distribution. See in this figure, this is normal distribution 1, k equal to 1. This is normal distribution k equal to 2. Now we are considering a problem in which the data instances or the training examples are generated by a probability distribution that is a mixture of these two normal distributions. We are taking an example. Okay. Now this problem setting is illustrated in this figure for the case where k equal to 2. Here the number of normal distributions we are considering is 2. That is why k equal to 2 is taken. And where the instances are the points shown along the x-axis. So these are the training examples, 1, 2, 3, 4, 5. All these points along the x-axis are the training examples having normal distribution. But they are found to have two types of normal distributions. And we doesn't know from which distribution they are actually coming. Okay, some of them are following this distribution and some of them are following this distribution. So which distribution has the maximum likelihood of occurring in association with these training examples? Okay, now each instance is generated using a two-step approach. What is the first step? One of the k normal distributions is selected at random. And second, a single random instance xi is generated according to this selected distribution. Now we are just generating some random data in order to study this EM algorithm. Now when the random data is being generated, in the first step, one of the k normal distributions is selected at random. You can just select one of those distributions at random that the data is falling into this normal distribution or it is drawn from this particular normal distribution. Now second step, a single random instance xi means one single training example is generated according to this selected distribution. Okay, now according to selected distribution, say it is distribution 1, k equal to 1. Now we are generating an instance according to that particular normal distribution. The data will be according to that normal distribution. Now if you take another normal distribution k equal to 2, generate data according to that particular normal distribution. Means that instance doesn't have any extreme values. It is having values according to the normal distribution that is observed. Now this process is repeated to generate a set of data points as shown in the figure. Now this two-step process is repeated again and again in order to generate sufficient number of data points. Now to simplify, let us consider the special case where the selection of single normal distribution at each step is based on choosing each with uniform probability. Uniform probability means either selecting first normal distribution is having 0.5 probability and selecting the second normal distribution has again 0.5 probability. Means they have equal probability of being in accordance with the data points. That is how we select it. It is not that we are arranging our data in accordance with one particular normal distribution. We are drawing data such that we should get a doubt that they have been derived from both of the normal distributions. This data's distribution applies to k equal to 1 or even k equal to 2 is also explaining the distribution of the data better. We doesn't have idea now whether this data is drawn from k equal to 1 distribution or k equal to 2 distribution, where each of the k normal distributions has the same variance. You know how to calculate the variance, right? From standard deviation. You know how to calculate the standard deviation also. You remember how to calculate standard deviation? You take the mean of the values and calculate each sample points difference from the mean, square it, divide by n, you will get the standard deviation. Now square root of the standard deviation, you will get variance. Okay, that is basic mathematics. Now, where each of the k normal distributions has the same variance sigma square and where sigma square is known. Now, you're taking the two normal distributions and you're generating the data points such that the data points will be suitable for the first normal distribution as well as the second normal distribution. But we doesn't know exactly from which distribution it is exactly drawn. And these two normal distributions are said to have the same variance also. So we doesn't actually know from which normal distribution the data is drawn. Now the learning task is to output a hypothesis H equal to mu1, mu2 and so on up to mu k, the means of the normal distributions that describe the, that is what is written here, that describes the means of each of the k distributions. Now, the learning task is to output a hypothesis by calculating the means of each of this distribution. K equal to 1 distributions mean, k equal to 2 distributions mean. Now, we would like to find a maximum likelihood hypothesis for these means. Which mean is more likely? We can say from that normal distribution that unobserved data has been derived. If we know the distribution, you can easily guess the unobserved values. Okay, that is a hypothesis H. What is the maximum likelihood hypothesis? The probability density function here. P is taken as small p, lowercase p. So it is called as probability density function, not probability mass function. So we would now like to find a maximum likelihood hypothesis for these means mu1, mu2, mu3 and so on. Because we have only two distributions, our hypothesis is to find the maximum likelihood of these two means. But if you have many normal distributions, then you have to find out from that set of means which is having the most likelihood. Now, that is a hypothesis H that maximizes this posterior property of observing the data given the hypothesis. Okay, now it is easy to calculate the maximum likelihood hypothesis for the mean of a single normal distribution given the observed data instances x1, x2 and so on up to xm drawn from this single distribution. Okay, you're trying to find out the maximum likelihood for the mean of this particular distribution by considering the data instances. We already know that the maximum likelihood hypothesis is the one that minimizes the sum of squared errors over the m training instances. What is the maximum likelihood hypothesis? Which reduces the prediction error, right? You know that, which reduces the prediction error. Say the training example has one target label and some other target label is being predicted. What is the difference between these two? If you can reduce the difference in the prediction, you are minimizing the prediction error, which will maximize the likelihood of that hypothesis. Which is your best hypothesis? Which reduces the prediction error is your best hypothesis, like maximum likelihood hypothesis, maximum a posteriori hypothesis. Correct? So we already know that the maximum likelihood hypothesis is the one that minimizes the sum of squared errors over the m training instances. For every training instance, a prediction error has to be calculated and summed up. Now that value should be as much low as possible. And that will be your maximum likelihood hypothesis. So now our problem, how can we represent it? You are calculating the mean. Now what is the maximum likelihood of the mean of a distribution? You are minimizing the sum squared error of the predictions. Xi is your original data, training data that is given. Mu is what is calculated. Now the difference between them should be minimized in order to reduce the prediction error, which will give you the likelihood of that mean for the normal distribution to be more. Okay. Now in this case, the sum of squared errors is minimized by the sample mean. So you can simply write it as, so instead of sum of squared errors, you can write it as sample mean itself directly. Now, if the sample mean is calculated, it is same as the normal distribution's mean also. So there will not be any difference. So that will be the maximum likelihood. So we have transformed our maximum likelihood of the mean to be just addition of all the sample points from 1 to m divided by the number of sample points. That is nothing but the average or the mean of the sample points that is taken from the normal distribution. Right? Now our problem here involves a mixture of k different normal distributions, and we can't observe which instances were generated by this distribution. Did you understand now the problem? Now, initially it will be like completely vague, but as you go on, you will understand the concept very well. Do not get confused or do not lose interest if you don't understand in the first instance. Okay, slowly as you go on with the steps, somewhere it will trigger the understanding for you. That is why I want you to stay focused during the class. Now see here, it will make it more clear. Our problem here involves a mixture of how many distributions we have, how many distributions we are considering, k different normal distributions. We have taken k equal to 2 because we are considering two normal distributions, one like this and one like this in the figure. Right? You remember? Now our problem here involves a mixture of k different normal distributions, and we can't observe, still it is not clear which instances, means instances plotted on this x-axis, which instances were generated by which distribution. We have just drawn the instances from these two normal distributions, but which instance is generated by which distribution is not clear. Until unless you know the distribution from which a sample point is drawn, you can't guess the unobserved data. Okay, thus what we have modeled now is we have a prototypical example or a model example of a problem involving hidden variables. Got it now? We are slowly arriving at the problem of hidden variables. Some of the data is known, some of the data is unknown. Now our task is to know our task is to calculate the unknown data from the known data by using expectation maximization algorithm. Now in the example of this figure, we can think of the full description of each instance as the triple. What is the triple? What does it contain? The observed value xi and zi1 and zi2 indicate two normal distributions used to generate the value xi. What is the problem now? What problem we have now to solve by using expectation maximization algorithm? You have a training instance xi and you have two distributions zi1 and zi2. But you doesn't know xi comes from zi1 or zi2. Got it? Now in particular, zij has the value 1 if xi was created by the jth normal distribution. See, it is clear now. In particular, zij has the value 1, means zi1, if you're considering, it has the value 1 if xi was created by zi1. Other way, say if xi is created from zi2, then zi2 will have the value 1. Otherwise, it will have the value 0. Means you are indicating mathematically. If xi has been generated by this distribution, zi1 will have value 1. But if xi has been generated by this distribution, not this distribution, in that case, zi2 will have value 1 and zi1 will have 0. This is the triple you are trying to find out now. Here, xi is the observed variable. Xi is observed in the description of instance, and zi1 and zi2 are hidden variables. We doesn't know from which normal distribution, whether it is zi1 or zi2, that xi has been drawn. Now, because xi is known, by learning the distribution of xi, we can guess whether it has been generated by zi1 or zi2. Now, if the values of zi1 and zi2 were observed, we could use the equation. If at all they are observable, we could normally use this equation. Our maximum likelihood of zi1 or zi2, which is having the maximum, like the mean of which distribution, either mu of this or this, the mean of first distribution or the mean of second distribution, which is having maximum likelihood to have generated the sample point xi. Did you understand? What is the maximum likelihood of sample point xi being generated from mu1, from zi1 distribution or zi2 distribution? Say, for example, if zi1 distribution, zi1's distribution's mean has the maximum likelihood, we can say that xi has been derived from zi1 distribution. Otherwise, say zi2 distribution's mean has the maximum likelihood, has maximum probability. In that case, we say that the training instance xi is derived from the distribution zi2, not zi1. Okay, that is the problem now. Now, if you know the means of both the distribution, assume if the values of zi1 and zi2 were observed, we could use this equation mu maximum likelihood to be arg minimum of, you are trying to minimize the prediction error, square of the prediction error, sum of square of the prediction error. Okay, to solve for the means mu1, you can easily calculate mu1 and mu2 if zi1 and zi2 are known. Because they are not known, we will instead use the expectation maximization algorithm. I think the problem is now completely open for you. Initially, you might have wondered why we are using normal distributions, why we are generating sample points. Now the problem is very clear for you. If the values of the normal distributions, means if the mean of those normal distributions were observed, we can easily know that which of the normal distribution generated this sample point xi by calculating the sum squared error and minimizing that sum squared error. Whichever mean minimizes the sum squared error or the prediction error, that mean is maximum likely. So that we can say that mean or that distribution is the distribution from which the sample point has been derived. But we doesn't know zi1 and zi2. So we can't calculate their means. So what we have to do, use the expectation maximization algorithm. Now apply to the problem of estimating the two means for the figure. The expectation maximization algorithm first initializes the hypothesis to h equal to mu1, mu2. Hypothesis now has two options. Mean of first distribution, mean of second distribution. But you doesn't know which of these means has the maximum likelihood, which of these means has the highest probability to have generated this sample point xi. Okay, so we are just assigning h equal to mu1, mu2. Both of the means you are assigning. They have equal probability of generating this xi initially. We haven't still found out their maximum probability. Both are equally probable of generating this xi. It then iteratively re-estimates the hypothesis h by repeating the following two steps until the processor converges to a stationary value for h. Now, as you go on calculating zi1 and guessing, not calculating, guessing zi1 and zi2, if your guessing is correct, it will stop. If it is still not correct, in order to assign some maximum likelihood to either mu1 or mu2, it will iterate again and again. Again and again, it will guess the values of zi1, zi2, expects the values of zi1 and zi2, and try to maximize the hypothesis. If the hypothesis is not maximized, again in the next iteration, Zi1 and Zi2's values are guessed, and once again the hypothesis maximization is found. If the hypothesis is not maximized, again it goes to the next iteration. But if the hypothesis reached its saturation point, where no longer it can improve, that is the point of convergence. What is the first step? Calculate the expected value E of, see the representation, E of Zij. Means you're calculating the expected value for Zi1 and Zi2, the first distribution and the second distribution. Mean of first distribution and the second distribution, okay, of each hidden variable Zij. Normally we have here two distributions, but in some extreme cases you may consider many distributions because you don't know from which distribution the data point is drawn. You wanted to learn the distribution, right? So calculate the expected value of the mean of Zij of each hidden variable Zij, assuming the current hypothesis H equal to mu1, mu2 holds. Now what is your second step? These expected values we have to check. Calculate a new maximum likelihood hypothesis H dash. See the new hypothesis. Your old hypothesis is H equal to mu1, mu2, the mean of both the distributions. Now the new maximum likelihood contains the new means for the hypothesis, assuming the value taken on by each hidden variable Zij is its expected value E of Zij, calculated in the first step. Now what is your next task? Replace the hypothesis. This is your old hypothesis. Replace it by the new hypothesis and iterate. Now let us examine how both of these steps can be implemented in practice. What is done in the first step? Step 1 must calculate the expected value of each Zij. The mean of each of those distributions are calculated. Now this expected value of Zij is just the probability that instance xi was generated by the jth normal distribution. Okay, you are just expecting the probability of this sample point being generated from the first distribution Zi1 or being generated from the next distribution Zi2. Now how can you represent this mathematically? Probability of x taking the value xi given the mean of j, means given the mean of first distribution and given the mean of second distribution, divided by probability of x taking the instance, assuming the instance as xi, given mu equal to mu n. Sum up all their values and divide. Okay, now how do you represent this? You know the formula for Gaussian normal distribution. It is given in your fifth module in a table. The Gaussian normal distributions formula is 1 by square root of 2 pi sigma square into e power minus 1 by 2 sigma square xi minus mu j whole square. Okay, this is the formula for normal distribution. Because these two distributions are normal distributions, you substitute that, but we have omitted this part because it is a constant for simplicity. Okay, so you get e power minus 1 by 2 sigma square multiplied by the squared deviation from the sample point, the square deviation of the sample point from the mean of that distribution whole square. Okay, divided by the same term you are using here. Thus, the first step is implemented by substituting the current values of mu1 and mu2 and the observed xi in the above expression. Now in the second step, what you do, we use what is the expected value calculated during step 1 to derive a new maximum likelihood hypothesis h dash equal to mu1 dash. Note it as mu1 dash and mu2 dash. Okay, I forgot to add this complement here. Okay, this is the new hypothesis that is calculated h dash equal to mu1 dash comma mu2 dash. Now the maximum likelihood hypothesis in this case is given by How do you calculate the maximum likelihood hypothesis? It is nothing but the weighted average. So what is the expected value multiplied by the sample point divided by the sum of all the expected values? Okay, that is taken as your new mu that is calculated. Now, this expression is similar to the sample mean that is used to estimate mu for a single normal distribution. Okay, now our new expression is, now this expression what we have given is just the weighted sample. As I said, it is the weighted sample for the mu j, with each instance weighted by the expectation E of Zij that it was generated by the jth normal distribution. So you have the expected value multiplied by the sample point, sum up all those expected values divided by the total sum of expected values. That is called as the weighted sample mean. This expression is called as weighted sample mean. Why? Because you're multiplying the sample point with the expected mean of that particular distribution. E of Zij means what? Mean of that distribution. Average of all the values. Say I'm using a bell curve to indicate weights of 80 students. Now average weight of those 80 students is expected value of Zij. That is multiplied by the new sample point now, what we have taken, to understand whether it has been derived from this distribution or not, divided by the sum of all the expectations. That will give you mu j. Now this algorithm for estimating the means of a mixture of k normal distributions illustrates the essence of expectation maximization approach. What it does, the current hypothesis is used to estimate the unobserved variables, and the expected values of these variables are then used to calculate the improved hypothesis, right? Now it can be proved that on each iteration through this loop, the expectation maximization algorithm increases the likelihood of probability of D given H, unless it is at a local maximum. Means it will try to increase the likelihood of average of the normal distribution unless it is at a local maximum. It has reached a local maximum point where it will start converging. Means it will become stagnant. No more improvements can be brought. That is called as the point of convergence. Now the algorithm thus converges to a local maximum likelihood hypothesis for mu1 and mu2. Finally, you can find the final maximum likelihood for mu1 and mu2. Whichever is having the highest likelihood, we can say that xi has been derived from that normal distribution. Say mu1 is having maximum likelihood, then xi is drawn from the distribution 1. If mu2 is having maximum likelihood, means highest probability of being true with the given data or the sample point, then you can say that xi has been derived from mu2. Mu2, that is second normal distribution. Now in this module, we have learned what is the Bayesian learning and how it is used to draw inferences with some support or confidence, and the Bayes theorem in association with concept learning, and the maximum likelihood and least square error hypothesis, and the maximum likelihood for predicting the probabilities, and minimum description length principle, how simpler hypotheses are preferred over complex hypothesis, and naive Bayes classifier, how conditional independencies should be considered while classifying using the naive Bayes method, and Bayes belief networks, how you can attach probabilities to the child nodes given the parent nodes probabilities, and finally the expectation maximization algorithm. I expect you to spend more time on this expectation maximization algorithm. Why? Because it is little confusing. So the basic notion, if you understand, you can apply it to any type of problem. The problem that has been discussed here is little complex, but the basic notion what I have explained in the beginning of the class is very easy, right? So that idea you have to keep in mind while understanding this EM algorithm. Okay, any doubts in this chapter, students? Did you understand this concept? Okay, then we'll meet in the next class with the new module.